then its new radius is 1 over r. So that's the conceptual thing that we have to accomplish. And that's the only place you can move that 0 to make it minimum phase and not affect the amplitude, the magnitude. So the magnitude response is preserved. And you might remember that the magnitude squared can be thought of as the real function you get around the unit circle when you have both the minimum phase and the non-minimum phase zeros present. That's just an interpretation. It's the analytic continuation of the magnitude response squared on the unit circle. That constellation of poles and zeros at both r and 1 over r for each one. So we want the minimum phase ones. How do we get them? Well, we could factor the numerator and reflect them all in. That's one thing we could do. The impulse response is a big FIR filter. You could just think of it as a giant polynomial, factor it, and reflect everything inside. But good luck, right? Because impulse responses can be many, many thousands of samples long in a practical audio situation, and we can't factor polynomials that big. It's just numerically infeasible. Now, there are some really good high-powered methods for polynomial factorization. I recommend that you look into, this is in the topic of numerical analysis, and there's some great papers on that stuff. And of course, all of our root finders in MATLAB and elsewhere are going to be good, solid, state-of-the-art root finders. But you may find that it only goes up to a few hundred. So you have to do something else. So this would be the parametric method, where you factor it and reflect it back in. Parametric method, and also the definition, really. So I'll say parametric method and definition. That's really what we're talking about. But what we're talking about in the Cepstral method is a non-parametric method. So non-parametric. That means we're not going to factor anything. We're never going to see the poles and zeros. We don't know what they are. We're just going to make them minimum phase in principle. And so remember the definition of this method. It is let's call it H minimum phase is defined as, and I'll call it H hat minimum phase because it's not going to be exact. It's a function of omega, really omega sub k, but you'll get that, right? So then we're going to define that as e to the, so what are we going to have? We're going to have e to the inverse FFT. I've got to think about my notation a little bit. Well, I showed it to you in MATLAB last time. Should I write it in MATLAB? Maybe I should write it in MATLAB. So we'll start with H hat, which is non-minimum phase in the middle. And then first we will take its absolute value. And then we're going to take a log. I don't care what kind of log, as long as you invert it correctly. So that gets us to the log magnitude spectrum. And then if we inverse FFT that, we're going to have a Cepstrum. All right, O. And you all know this from the spectral smoothing stuff. We're going to actually need the complex Cepstrum here. So get rid of the absolute value. And just to highlight what this means, we're going to have the absolute value here, log, plus j times theta of omega, right? I should put a hat on it. In other words, the only difference between the magnitude and the complex is, the complex is the magnitude times e to the j theta. And so when you take the log, then the e to the j theta just goes off as an additive term that is the j theta part, right? Maybe I should say that this is h hat times e to the j theta of omega. And then the log turns that multiplication into a sum, and it turns this exponent into a multiply. Or you could just say the definition of log is it's the exponent of e. So this is obviously log base e. I should say that. Probably should have used ln. All right, so now we've got the log spectrum, and now we inverse transform it. So maybe I should say, I'm running out of space, so I want to say F inverse like this. So that means inverse Fourier transform. And then we have to fold it. So Now this is something that's in the lecture videos. I haven't derived it independently in class. It's in the book, it's in the lecture videos. But let me just summarize what's there. And that is that in the time domain, the Cepstral domain, the complex Cepstral domain, you've got exponential decays for every stable 0. So that's just one. I'm sorry, stable pole. And you have exponentials of an opposite sign for every minimum phase 0. But we don't have any unstable poles by assumption. But we will have minimum phase zeros. And so if there's any exponent going to the other side, that's the non-minimum phase 0. Okay, so this is...
I like where this is going, but I don't really understand what those lines on the graph mean, why they're zeros and why they're poles. Can you elaborate on that?
This is the image in the Cepstrum, the complex Cepstrum of a stable pole in the impulse response. And I'm actually not sure about the sign. I might have them flipped. It may be minus exponentials for all the poles and plus exponentials for all the zeros. I haven't reviewed the videos. None of us have seen the videos.
These are going to oscillate, or?
Yes, yes.
Look like a decaying thing?
Let's look at one term. It's an exponentially decaying thing, but let's look at what it is. Let's look at one term in the Cepstrum. It's going to be the inverse Fourier transform of log of, what do you want, a pole or a 0? A pole? All right, so we'll have one stable pole, 1 minus r z inverse. So it's a pole at r, and let's let r be complex so it can oscillate for generality. And so now what we need is so the way you derive this is you basically find the series expansion of this. Does anybody know the series expansion of log by heart? It's some exponentially decaying thing, right? It's what I drew as this. Oh, I'm sorry. That is where it's added. So if you have this exponential decay and it's all summed together, then the inverse transform just erases the sums. So I think I should just go to the derivation in the text. It's just right there. I can just put it up in front of us. Instead of, because the next step for me to do is to derive the Taylor expansion for log of 1 over 1 minus x. And that will take us a good solid 15 minutes. And so let's just look at it.
Yeah, let's keep this.
Well, it's worth just looking at, I think. And theoretically, we've all seen it. We've all studied it carefully in the text and watched the video derivations in detail. That's in principle, but we have such terrible memories. We have to remind ourselves again and again. I actually did the derivation and don't remember, so. Let's see. Okay. Got the wrong one there. So let's go to, let me just navigate while that's getting it together. Where?
The series expansion of log of 1 over x? Is that?
Yeah, we need the series expansion of log of 1 over 1 minus x.
Yeah, I'll show us the video with the links were broken. The 2 links were pointing at the same video.
What? I'm sorry, I couldn't understand.
2 of the links are pointing to the same video.
Is that right? Okay, well, you got to email that stuff to me because I will fix that as soon as you tell me. So let's go to Cepstral, poles and 0, conversion to minimum phase. So wait a minute. Where's? Oh yeah. It's in the chapter on minimum phase, isn't it? It's in this chapter. Am I not? Okay, I am. Minimum phase filters.
It's probably creating minimum phase.
Well, I'd kind of like to show you the math. All right. I know it's in here. I know it. Minimum phase polynomials. Here's the all pass example. This is very surprising. I guess I need to review it myself, find out where it is. Okay, what's the... let me have a cut in the video because this is